welcome back to the Futureprint Tech Fest. Our next session is delivered by two people from Fujifilm Ink Solutions Group. The session is entitled How to Optimize Inkjet Productivity and is presented by Dr. Barry McGregor and Angelique Runacre. This session will explore the interface between the ink chemistry and engineering in creating the right solutions to optimize productivity. They'll discuss the considerations and challenges to productivity and explain some of the benefits of a multidisciplinary approach to ink and system. So I hope you enjoy the next session. Thank you.
I'm Angie Runacre, the Technical Manager at Fujifilm Ink Solutions Group. I've been working in the inkjet ink industry for over 20 years now, initially working as a chemist formulating UV curable inks for wide format graphics, printing applications, and now leading a team of chemists who are developing inks focusing on single pass printing applications such as packaging. It's been a great time working in this industry, and over the years I've had the pleasure of working closely with my colleague Barry McGregor. He's a serious physicist, which is a great compliment to the chemistry that's going on here. So I'll hand over you, Barry, to introduce yourself.
Okay, thanks, Angie. So my name is Barry McGregor. I've been working with this company for over 12 years, but I've spent much longer in INKJET, and my role is slightly different for an ink company. I work as the integration manager in charge of a very small research facility in Cambridge, and our focus is predominantly on the integration of technology into print systems to make sure that we get optimal performance out of our inks and that customers achieve the best of the capabilities that they can with our products.
Thanks, Barry. So thinking about today's topic, I think you'll agree that the thing over the years when we've done various trade shows and conferences, most people ask us is how fast can inkjet go? Because they're thinking about how it can fit with their processes and they can actually make money from it. But it's really a difficult question. And to answer that question, I think what we really need to consider is productivity. From my own perspective, the answer on how to optimise inkjet productivity, it can fall into two camps. There are those people that the process is new to, and it's about them making the right design choices to get a system that gives them the productivity they need. And then there's the other camp, those with more experience with inkjet, that are really looking at how they can look at ink and system to really optimise their existing processes. But I don't know, what's your take on that, Barry?
Yeah, I'd agree, Angie. When we talk about productivity, people do tend to focus on speed, but it's about so much more than speed. But speed in itself is a whole mesh of different parameters. So to take an analogy, if we were to look at cars, the speed of a car is a mixture of lots of different properties, such as the model of the car, the size of the engine, the fuel that you put in the car, but also the road it's travelling on. And just the same as with inkjet, the speed of inkjet is a whole mashup of lots of different parameters that come together. And that's things like the print head, the print engine, the ink that you put inside of it, but all of those peripheral systems that come together to give you an ultimate speed. But it's not just about speed. There are many other factors that need considering.
Yeah, I'd agree with you, Barry. I think, my first reaction is it can go as fast as you want it to go, as long as you're prepared to pay for it. But will it give you what you need?
Let's return to the analogy of using cars to look at speed. Okay, so we're all impressed by fast cars, but we don't all drive Maseratis. And the reason for that is that they're impractical. Okay, but let's take that analogy to the absolute limit. So the fastest car ever was the SSC Thrust, which in 1997 achieved a top speed of something like 750 miles per hour. Okay, so that's the world's record, okay, with it. But to achieve that, it took an investment of what would now be $4.6 million, and it took over 5 years to develop. So even if you were prepared to put a huge investment in, then you wouldn't necessarily choose that as a technology that you would adopt going forward, because even after all of that investment, you'd end up with a system, a car in that case, which would only travel for 1 mile and would be a nightmare to park. And we can use similar analogies with INKJET to explain how productivity can be optimized.
Speed is just about how fast you can print something. So when you think about that print speed and then what you've paid to get the printer and the associated technology to do this inkjet printing, you're talking about a production unit cost. And that's got to be commercially acceptable for the run of the job. And also, considering there may be other additional sort of non-cost related benefits that can add in to why you would choose this technology. But it has to be viable. And another thing we must consider is image quality, as well as the production unit cost, as well as the application suitability. It's got to be acceptable. Someone's got to want to buy what we're producing.
You're right. And traditionally, when most people begin this journey into looking at what system would suit them the most, there tends to be a default starting point, and that's where people tend to focus on a technology which you can pick up and hold and examine and look at data about, and that's the print head. And the reason behind that is that people can see it as the core of a print engine, and quite rightly believe that if you choose the wrong print head, then you could handicap your entire system, so that then you're limiting your productivity overall. And whilst that's an acceptable way to move forward, I think those people with maybe more experience in different applications in our fields are drawn to the conclusion that actually we need to start thinking from a different perspective and focus on the ink first. To begin considering how we optimize productivity in a system. And that could be seen as bias, and I accept that. But remember, it's from a whole round view and from many years of working together, that we draw that conclusion, with it. So what we think as integrators is that ink is the natural starting point. After all, it's the only part of the system that actually leaves on the product. So whereas choosing the print head incorrectly can actually limit your productivity, the consequence of choosing the wrong ink for your system can be far greater, in that you could end up with products which aren't fit for purpose. So it doesn't really matter how productive a system is if it's not delivering the right product to the customer.
Yeah, ink technology selection is absolutely key to defining the speed and hence the productivity. And when we think about the different types of ink technology and the way they're drying, you've got absorption, you've got phase change, you've got evaporative, and you've got irradiation technologies. And all of these have got different mechanisms and therefore different associated timescales with the rate at which they can achieve this drying and hence productivity.
So in your view then, Angie, which of those techniques is the most suitable for inkjet industrial applications?
Well, we're talking single pass, and absorptive and phase change hasn't really gained any traction for a variety of reasons. So I think it makes best use of the time to really focus on evaporative and irradiation drying processes. Evaporation is likely the drying process people are most familiar with. It's very akin to absorption processes, but typically this is on media which is not quite as absorptive. So you're relying on evaporating the ink carrier and leaving the colourant and the film properties behind on the film. So this means there is a big requirement for drying off the bulk of that ink film. And typically processes like infrared dryers, other thermal dryers, air knives are employed to carry out that process.
Yeah, absolutely. And from a physics point of view, it's important to keep in mind that irrespective of which drying technology you use, there's intrinsic limitations which will limit that drying process in itself. So for instance, if you take water and organic solvents, then water, because of the vapor pressure associated with it, will typically take around about 15 times longer to dry than organic solvents at around about the same temperature, 40 degrees C. Now, obviously, you can change the temperature and change the rates of evaporation, okay, but it will always turn out, because of those physical limitations, that you will need more energy to be able to dry aqueous inks than you will organic solvent-based inks. And that puts some constraints on the drying systems themselves. So for aqueous inks, you're going to typically need either hotter dryers, in which case you may have some limitations that arise from the type of media that you're pushing through it if you've got a very thermally sensitive substrate. Considering the amount of time that you have to expose the substrate to in the heater, so you could end up with very long heaters, in the aqueous case as well. So if you take just purely the energy of drying, then aqueous could be much more expensive to implement. However, with solvent-based inks, of course, you've got to take into account the cost of reclamation, because in the modern ethical environment, we can't just pump those solvents out into the air and leave it for somebody else to worry about. So all of these different drying mechanisms have consequences which we've got to take into account when choosing a technology.
Absolutely, Barry. And when we're formulating solvent-based inks, we can get the productivity by using solvents with that higher vapor pressure and get that rapid drying that we need to hit the production target. But there's two drawbacks with that, as you've alluded to. And the first one is that these high vapor point solvents, they have a lower flash point. The flash point is driven down. That creates two issues: transportation of the product and also use of the product. Using flammable products in an environment with a lot of electrical activity going on is a definite no-no. So there is a definite balance there.
As you mentioned there is a second point, which is the consequence on the system. So we can't keep using solvents which evaporate even more rapidly, because the printheads themselves have apertures, the nozzles on them, which are typically 10 to 30 microns in diameter. So whilst we want rapid drying on the surface, what we don't want is rapid drying in the printhead itself, which then causes blocked nozzles and limits the lifetime of the printheads. Fortunately, nowadays, though, techniques have come across to try and combat that, which allows us to use solvents or liquids within the inks, which are more volatile. And that technology is recirculating printheads, which makes sure that we refresh the ink in the nozzles by having a constant flow of fresh liquid going past those nozzles, so that the dry material can't build up within them.
To be honest, whatever technologies using solvent or aqueous, with evaporative drying, there is another problem that we haven't mentioned, and that is the film deposition. If you think about a flexographic ink, you're putting down about 2 grams per square metre of ink to achieve your target density and gamut. Unfortunately, we're not able to include so much pigmentation in an inkjet ink because of the viscosity limitation, and typically we'd end up putting down 10 times the amount of ink to achieve the same optical density as those analogue processes, which therefore, if you drive forward, means you could predict that you might need 10 times more energy or 10 times more effort to drive off the carrier, the evaporative material. There are ways to combat that. For example, ensure we get good dot gain is one method, and also using colour profiling to make sure we're not overcompensating, putting too much ink down when we don't need to. But it's a really interesting point. And Barry, can you explain why we don't just load the ink up with as much pigment as we can to try and reach those targets?
Yeah, you're right. And it's one of the features of inkjet heads themselves, in that the fluid channels inside the print heads are very, very small, because they've got to deliver a lot of fluid to a lot of small apertures, which means that to actually be able to transmit enough fluid through those channels, the inks themselves have to be a reasonably low viscosity. And we're talking of the order typically between 5 and 25 centipoise. And that has quite a few consequences, in that when the ink hits the surface, it remains at that viscosity. Okay, so there are some inks which will thicken up slightly in contact with the surface as it changes temperature, but that's nowhere near the size of that's nowhere near the magnitude of viscosity that you have with flexographic inks, which are hundreds of centipoise in viscosity. And that has a consequence, because when the ink is on the surface, it's able to migrate, and that migration is related to the viscosity of the ink itself. Okay, so that's why inkjet inks are more susceptible to bleed at the same temperature than similar flexographic inks.
That's a great discussion there, Barry, and I think it just summarises why we feel it's so important to work together, because we've got this problem with evaporative technology where you're trying to balance that rapid pinning, that rapid crisp image quality fixing with fast drying on the substrate, but we don't want that happening in the printhead because we're trying not to block nozzles. And I think that's where the synergy between chemistry and physics comes in. We've got the ink capability to balance that as best we can, but then we've also got the system factors, for example, longer drying tunnels, some of these other processes that you've mentioned and know very well, where we can bring the two factors into play to optimise that productivity with this technology.
The overriding message, as far as I can see, with evaporative printing is not to be tempted to aim for too high a speed or productivity in that case. So returning to the car analogy again, if we consider a printhead and we want to run that printhead at its maximum speed and then tune everything around the system to always operate at that maximum speed, it's equivalent to putting a Maserati engine in a Robin Reliant. Okay, so no matter how much we run that engine and that engine has got the capability to go to high speed, if it's not surrounded by the same peripherals, then it will never achieve that same speed. So for instance, with the Robin Reliant, we'd have to add an extra wheel. We'd have to make the car more aerodynamic. We'd have to increase the brakes. And in the end, what you'd end up buying is a Maserati, rather than having your Robin Reliant running at what's optimal, okay, within there. So it's better to consider the economics of the entire package and aim for what's right for the process rather than be drawn into headline speeds that individual pieces of hardware can give us. It really is a holistic view of inkjet printing.
And obviously we can see from the application of evaporative technology in inkjet processes that it can give good productivity at a reasonable cost, as you say, Barry. But there's one other thing worth mentioning, and that is things like the RAPIC technology, where you're able to use specialist evaporative technology, where you have pigment particles stabilised in a system that are jetted onto a substrate. Once they hit that substrate, the pigment destabilises and crashes out and fixes. The viscosity rapidly increases. You get that lovely crisp image without the requirements of such a quick drying time or getting that carrier out, and therefore you're able to achieve high productivity with this technology, again at a reasonable cost.
You're absolutely right, Angie, and that RAPIC technology is a very elegant solution to a very difficult problem, which allows us to get into those higher productivities. And again, what you're doing is you're reducing the time scale of the drying process, as you mentioned. But we all know that there's another technology which has an even shorter time scale for fixing, and you're an expert in that. So can you explain a little bit around that technology for us?
Definitely, Barry. I'll take that one. Thanks a lot. Yeah, so irradiative drying, it's the opposite of evaporative drying. It's really completely different in terms of the timescales. It's instantaneous. And what happens is you have a liquid that contains material that can be polymerized in the presence of a UV irradiative light source. That light source hits the liquid. Within the liquid there are chemicals that are cleaved. Free radicals are generated, which then attack the monomers, the pre-polymers within that chemistry, creating active sites to allow them all to join together and bond. So it really can be an absolutely instant process. And of course that means that we have drying instantly. So productivity can be fantastic with low energy cost.
There's two main ways of producing UV for curing UV curable films. You've got the medium pressure mercury arc lamps, and you've got LED. Medium pressure mercury arc lamps have been around for a long time, and they are well utilised in this industry. They deliver a very broad spectrum of output, and they deliver a very high dose over a reasonable footprint, and a very high brightness or irradiance. And that means that they can be used in many high-speed applications, and have been used in many high-speed applications really successfully. But they do have some well-documented drawbacks, and probably the largest of that is the high surface temperature of the lamps. So the lamps run at around about 800 degrees, and they need to run at that temperature to create the pressure inside the lamps that gives you the right wavelengths. Now, in a lot of applications, that's absolutely fine, but where you've got a thermally sensitive substrate, of course, it can cause substrate damage. So what you have to do is use things like shutters, those kinds of things, to be able to protect your substrates, because you can't just switch the lamps on and off. But over the last 10 years or so, there's been massive advancements in the performance of UV LED as well. And that's slowly beginning, well, not so slowly now, it's beginning to replace lots of applications where arc lamps would have been traditionally used.
These long wavelengths, if you think we spoke earlier about the thickness of an inkjet ink film, they're brilliant for penetrating deep into the ink film, so they can be great for getting that real adhesion at the base layer. The problem is, if you think about the irradiative curing process, you're using that UV light source to generate free radicals, which are joining those monomeric units together. Unfortunately, these free radicals can also react not only with the monomer, the pre-plastic in the liquid, but they can react with oxygen, and ink contains quite often levels of dissolved oxygen, which means to still get sufficient cure all the way through that film, your rate of oxygen consumption of those radicals must be less than your rate of radical generation by the power of the LED UV light. So surface cure can be a problem with LED curing light sources. This can be overcome by using very high-powered LEDs as one method.
So when talking about those issues of surface cure, LED technology advancement is certainly moving forward and helping us overcome that problem. So for instance, as you mentioned, we can increase the dose by increasing the power of the lamps, but the consequence of that is that we have to add more LED dyes into a lamp to increase that dose, and that has an associated cost increase with it. Other things that we can do, though, are begin to adopt the shorter wavelength LEDs that are beginning to emerge. And what they will do is specifically target the free radical generation in the surface and deal with that surface cure issue as though it were a medium pressure mercury arc lamp. And that probably is where the technology will end up. But at the moment, those LEDs are really low efficiency. Which means that they're not quite paying off yet from a development point of view as to allow us to do that surface cure at incredibly high speed. But the story doesn't end there, because there's other things we can do, and we don't have to focus just on the LEDs themselves. We can focus on things that support that LED action. And one of those is to introduce nitrogen inertion, which effectively removes oxygen from the cure zone. And if there's no oxygen, there's nothing to react with the radicals and prevent the surface cure. However, all of those techniques, increasing the number of dyes, adding new wavelengths of LED, introducing oxygen inertion, come at a cost. And whilst we've got the environmental message that comes with LEDs from their pure use, when you put it together as a package, you have to consider the overall cost to the system and the environment of putting those systems together. So it's all about a balance of productivity. And there will be some sweet spots, where LED plays a huge role and can really take advantage of that technology. But there will be some situations where arc cure, medium pressure mercury arc lamps will win out. However, it's not just a story of engineering, and that's why it's such a joy working with you, Ange, where we bring the hardware and the technology to a story which is only half the story, and you bring the other half. So I'll let you speak about that.
It's a good point, because that can be another way to reduce the LED cure cost, to actually look at the ink chemistry as a lever and a mechanism to do that. It could be considered a simple fix, and in some applications it can be. We can increase the reactivity of the ink to make it less requiring of such power to get the curing speed that you need for the high productivity. But unfortunately, many things in life are a trade-off, and quite often that will mean we have to sacrifice another property. For example, flexibility is one that's often associated with increasing cure response. You lose flexibility. And if you think about some of the single-pass applications like packaging, that could have a negative impact on adhesion or film formation around areas that have to be folded during that forming of the carton. But it is certainly another lever that can be used in conjunction with system modifications to drive that LED cost down, but it is very much application dependent. The good news is, though, that ink chemistry and raw materials and know-how is consistently and constantly evolving, and we do now have a lot more ways to increase our performance for these LED curable high productivity applications. The choice between arc and LED cure, it should be balanced then between what productivity we require and what application we require. And thinking about the ink chemistry and the system constraints, one thing I think is important to take home is that LED is often promoted as the right choice, the environmental choice, but actually when we consider all of the factors around LED cure and the additional requirements to get that productivity, that the energy required to achieve the productivity at high speeds, is not to go into that thought process blindly, but to really weigh up the pros and cons of arc versus LED curing. I think it's been a really good discussion so far, Barry. We've looked at the influence that ink technology has on print speed and the interplay between the peripheral components, what we can do with system, dryer, that kind of thing. But there are other tools at our disposal, aren't they? And I know a lot of these tools you could talk for hours on, Barry. They really are topics in their own right. But perhaps you can just give us a brief flavour of the scope of some of those considerations.
Sure, I think it's really important to reflect back as how we got into this story as well. So, as you remember, early on in this discussion, we were saying that most people start off with the print head and consider that as the speed limiting factor. And hopefully throughout this discussion, what people have been able to see is that actually there are many more influences, and a lot of those come from the ink, and they're not restrictions, it's about optimization. Okay, throughout that, and learning what's most suitable for your process, and not aiming for the sky, but aiming for what's right. And I think when we look at these other components, there's a huge raft of other things that we can consider which could impose a limitation on our productivity. So I think really the takeaway from me at this point is to say, yes, there is a whole world which I'm immersed in, which I consider daily about how those components affect productivity. But always it's by working in a team with guys like you, that it allows me to actually get to a real answer of what the productivity is, to a real solution. We've
really covered a lot of ground in this discussion. And I know, thinking back to the early years of my career in INKJET, the topics we've covered would have been considered revolutionary, but it's not now, is it? It's established technology. What we're talking about here isn't reinventing the wheel, but we'd really encourage anyone to come and see us at Fujifilm and to look at the products we've got on offer, that we can advise how they can be suited to your application, or if necessary, work together to develop a custom solution, really leveraging that physics and chemistry combination to get the productivity that you need.